arranque su conferencia. Quiero daros las gracias en nombre de la Asociación E3 Futura, ya que estoy arriba, de Editada Valenciana y de Telefónica, que han colaborado intensamente y duro, al igual que otros muchos patrocinadores, en que esta Campus Party sea una realidad. Sin ellos esto sería imposible y este momento también lo sería. Nosotros llevamos con la intención de traer a Neil Armstrong a la Campus Party 9 años, tantos como la Campus existe. Y desde los últimos 3, con una intención clara de conseguirlo, hemos estado persiguiéndole día tras día tras día, hasta que yo creo que por pesados lo hemos conseguido. Tenemos con nosotros a alguien que representa un momento que jamás se repetirá, jamás, nunca va a haber un segundo primer hombre que pise la luna, y yo creo que lo que nos va a contar es muy interesante. Va a hablar de el futuro de los viajes espaciales y de la energía que este mundo necesita para seguir adelante, que creo que son dos temas muy interesantes. Así que simplemente le voy a dar la palabra para que se suba aquí y esté con todos vosotros. Os pediré a la gente de prensa que, por favor, un momentito de fotos y ya arrancaremos la conferencia, ¿de acuerdo? I give the word to Neil Armstrong. Please come here.
No estaba preparado.
Bien.
Is it okay if I go through over there? Yes, it's fine, okay?
¿Va a hablarnos en el atril, que lo prefiere? Chicos, por favor, unos segundos más, la última foto y arrancamos, ¿vale? Ok, muchas gracias. Gracias por estar aquí. Vamos a arrancar la conferencia. Please.
I'm on my own. I'm on my own. Oh, this is great. Thank you, Father. Mr. President, distinguished leaders of the Valencia area and of science and technology in Spain, thank you so much for that marvelous warm welcome. I'm delighted to be a part of this campus party, where I understand this is in your 9th year of exploring the cutting edge of technical innovation. I will meander among the technical disciplines of science and engineering, not because I am an expert, which I am not, but it is an area in which I have spent much of my life, and because it's what I like. A few years ago, I was delivering a somewhat technical paper at a conference in Morocco. And in opening my lecture, I quoted an old Chinese proverb. At the break, I was approached by the permanent secretary of the Académie Française, who noted that the quotation I used was not Chinese, but rather Greek, Antisthenes, 5th century BC. The lesson to me was that no matter how well a speaker knows his or her subject, there is someone in the audience who will know it better. And I'm confident that will be the case here today. I'd like to spend our time together recalling a few memories of the past half-century and looking ahead to what it might mean in the future. I will certainly attempt to be factual insofar as an aging memory and the haze that obscures history will allow. Much of what you will be hearing will be information that you already know, but if I'm lucky, you will have forgotten. It has been said that science is about what is, and engineering is about what can be. Science is the eternal search for truth. One science that may not exactly fit that description is political science, and rocket scientists are rare. It is the engineers that create rockets. Science, Rudyard Kipling said it very well. He wrote, "I kept 6 honest serving men. They taught me all I knew. Their names are what and why and when and how and where and who." Engineering apparently escaped the notice of the poets. Engineers take the principles discovered in science and use them to create what can be. So let's start with science. A what is. What is the distance to the moon? Several decades ago, some astronomers proposed an experiment. The idea was deceptively simple. Compute the distance between Earth and Moon based on the time it would take for a beam of light to travel up to a mirror located on the surface of the Moon and be reflected back to Earth. Now, I wasn't one of the scientists on this project. I was a sort of technician. My job in the experiment was to install the mirror. After a 3.5-day trip to the site, I set up on the job of unloading the mirror. Actually, there were more than one. 100 mirrors to be precise, each a matched set, each about the size of half an orange. They were, more specifically, quartz corner reflectors, basically similar to the reflectors that are used in those traffic signs that shine so brightly when they are illuminated by your automobile's headlights. This experiment was possible only because of a quirk of nature, an astronomical peculiarity. Many of you will remember that on the Moon's surface, the daylight lasts for 2 Earth weeks. A day and a night is 4 weeks. That is, it takes over 300 hours for the sun to rise in the east, cross the sky, and set in the horizon in the west. But the Earth, it doesn't rise and set at all. It just stays fixed in approximately one spot in the sky, continually. From the Sea of Tranquility, the Earth hung above me 23 degrees west of the zenith, turquoise pendant against a velvet black sky. And if I could get the mirrors pointed directly at the Earth, they would always stay there, pointed toward Earth. Never have to be adjusted. Now, the light that was planned to be sent up from Earth was a laser beam. And the timing of the beam's return to Earth would be recorded by an ultra-accurate electronic clock. The theory propounded that the measurement would yield the distance to an accuracy of 28 centimeters. It may not be obvious why anyone would want to know the distance to the Sea of Tranquility within 28 centimeters, but we had to have some way of confirming our trip distance for our expense account. The experiment was initiated at Lick Observatory on top of Mount Hamilton near San Francisco, California. As soon as the mirrors were aligned, the scientists fired that laser. I thought they would have won. No. Those scientists were emotionally involved in this experiment. That laser pulse was precious to them. So when it did not get back home to Earth, they were puzzled. They sent up another pulse, and another. Nothing. They lost a lot of pulses that night. They were understandably distraught. They checked the big telescope they were using to catch the returning light and adjusted their equipment. Finally, success! A pulse. A few more adjustments, and more of the pulses were caught. To hit the mirror with a laser beam required precise pointing, equivalent to hitting a euro coin from a distance of 3 kilometers with a rifle. The problem had been their use in the pointing computation of the wrong latitude and longitude of the observatory. The same wrong latitude and longitude that had been believed to be correct since its construction in 1888. So the first result from the set of mirrors on the moon was finding the true position of Mount Hamilton on Earth. In the past half-century, we've increased our knowledge of Earth and the universe around us by an order of magnitude. Orders of magnitude. We thought the aurora borealis, the northern lights, was high-energy particles trapped by the Earth's magnetic field. Now we know that's not the case. We learned that the Earth has a magnetosphere and bands of radiation circling our planet. Our prior ideas of how the moon was formed have now been discarded. The consensus now believes that the moon was formed by Earth's impact with another celestial body about the size of Mars. Although it's true we have no eyewitness confirmation. We have learned that Jupiter has many more moons than expected. 70, I think, at last count. One of which, Io, who would have ever thought it, is the most volcanically active place in the solar system, while the neighbor Europa is covered with ice, probably hiding a liquidation. 6 months ago, a European space probe landed on Titan, the largest moon of Saturn, and sent back aerial and surface pictures. That is the most distant landing of any Earth-launched spacecraft, about 10 times as far away from Earth as is our Sun. Our probes have landed on asteroids and recently deliberately crashed into a comet. Much has been learned about the Sun. The relationship between the Sun's magnetic field and corona is understood. And the solar constant is no longer constant, which is a bit of an embarrassment. All of us have been introduced to the remarkable diversity and the spectacular beauty of distant galaxies thanks to the Hubble telescope. The birth and death processes of stars are becoming clear. 10 black holes have been identified in our own galaxy, the Milky Way. The Hipparcos satellite has positioned 120,000 stars to milli-arc-second accuracy. Indeed, this past half-century has been the most productive period of understanding the universe around us in all history. Yet, we have just scratched the surface. The unknowns far outnumber the knowns, and indeed, much might be unknowable. Now there is a program to return to the moon and journey on to Mars and explore beyond. Essentially, to sally forth and explore the universe. Now, some worry that this new exploration will be at the expense of science. But exploration, like science, is also finding what is. Not necessarily so careful or methodical or logical, but interesting and sometimes dangerous. While science and exploration are not necessarily exact synonyms, they are very closely related. Among other things in the new plan, the goals include returning humans to the moon after 2015, to send manned and unmanned explorations to Mars on a timetable that is yet unspecified. It is a long-term and long-range agenda for further exploration of our solar system. Not surprisingly, there are many opinions, a variety of opinions on the subject. Many support the plan. Others say we should bypass the moon and go directly to Mars. Some say, let robots do it. Some say, we shouldn't go at all. We need to take care of problems here at home. But before taking a position on such a matter, let's take a bit of time to look at some of the facts. First, let's compare the realities of leaving Earth to go to the moon and to Mars. Leaving Earth is relatively easy. Space is just 15 minutes away on a decent rocket. The moon is further, days away. Mars is quite a bit further. The trip to Mars takes months. The moon is always about the same distance away, about 400,000 kilometers, about a 3-day trip. Mars varies from 90 million to 400 million kilometers, depending on where Earth is in its orbit and where Mars is in its orbit. Departure times? You can go to the moon about any time, with constraints, lighting and trajectory and communications constraints. It's probably safe to say that each month you'll have a week or so that satisfactorily provides launch opportunities. Mars is a bit more difficult. You might think it would be desirable to go to Mars when it's close and the trip time is shortest. That trajectory, however, approaches Mars with a giant excess velocity, which requires a gigantic amount of fuel to burn to slow you down so you can land. The most fuel-efficient trajectory is called a Hohmann transfer, after the German engineer Walter Hohmann, who devised flight plans such as that 3/4 of a century ago. The trajectory requiring the least fuel actually requires Earth and Mars to be the maximum distance from each other, which requires a trip of 7 to 9 months one way. Take some books on tape along. This alignment occurs every 25 to 27 months, which is why you saw the Mars Spirit, the Mars Opportunity, and the European Beagle all departing Earth about the same time in late 2003 and all arriving at Mars about the same time last summer. You'll have about a 1-month launch window. If you miss that opportunity, you can unpack your bag, because you will have about a 2-year wait until the next scheduled departure. Now, there's some things about Mars you will like. It has a 24-hour day, almost like Earth, which you'll find comforting. It has a 687-day year, which is a real advantage for those annual burdens like tax filing and things of that sort. The gravity is a bit more than a third of what it is here on Earth, and you'll find that most pleasant. After you have arrived at Mars, and while you have been seeing the sights and sampling the cuisine, Mars and Earth have both been moving, and they're no longer in proper alignment for a return flight. So you might have to stay over for another year or so until the next favorable planetary alignment. You probably want to call home while you're there and tell your relatives what a great time you're having. In a call from Mars, your voice may take as many as 20 minutes to reach Earth, and the reply an equal time. So you ask your question, hang up the phone, and wait around until it rings 40 minutes later and get your answer. Actually, interplanetary telephone calls are about like email, and you'll get accustomed to it very quickly. You can begin to understand the problems these delays make for engineers who are controlling those robot rovers as they travel the Martian surface. Controllers must anticipate every move by a substantial length of time. We know that traveling to Mars is not easy, and we acknowledge that we do have problems on Earth. So let's talk about a couple. For as long as I can remember, it has been predicted that the world would run out of oil in 20 or 30 years. 20 or 30 years later, it was again predicted that we'd run out of oil in 20 or 30 years, etc., etc. Jerry McAfee, a knowledgeable oil expert, tried when he was the chief executive officer of the Gulf Oil Corporation back in 1979 to look ahead 20 years and predict the energy problems that we would be facing. He wrote, quote, "The world is not running out of energy, it's only running out of cheap energy." He thought crude oil production would peak sometime in the late 80s and decline to exhaustion sometime in the 21st century. By 1999, cars would have grown smaller and more efficient. Mass transit would have become the norm rather than the exception, and homes would be far more energy efficient. He thought the use of coal would increase, even though the 3 Mile Island power plant accident had occurred earlier that same year. He thought nuclear power would double certainly in the United States in 20 years, and even faster in the rest of the world. How did he do? Well, you might agree that we seem to be running low on cheap energy, at least at the electric meter and the gasoline pump. Crude oil production did not peak in the 80s. It continued to rise. Some petroleum geologists now think we are very near the peak. Others believe it's a decade or more away. Cars haven't shrunk much. Mass transit's still not the norm most places. Homes are not substantially more efficient. Coal usage does continue to grow as he predicted. Worldwide, coal burning releases nearly 10 billion tons of carbon dioxide into the atmosphere each year, about 70% of that from power generation, and that worries many people. The global warming controversy is well known to all of you. It's charged that greenhouse gases, principally created by human use of fossil fuels, is causing the Earth's average temperature to rise, eventually causing the melting of the polar ice caps and glaciers, which threatens to cause the sea level to rise and inundate shoreline property and put the ski slopes out of business. The opposition maintains the data are not persuasive. Temperature changes are within the bounds of the Earth's and the Sun's variation due to natural causes. And even if the hypothesis is correct, there's substantial geological evidence over 1.5 billion years to show that the natural condition is for Earth to be far warmer than it is today. The natural. It is with far less temperature extremes, hot or cold. And they say that would be true, that would be the condition today if it weren't for the fact that the Earth is still emerging from one of its rare ice ages. Both sides agree that cheap energy availability has been, since the Industrial Revolution, a key ingredient for most of human progress. Affordable food and an improving standard of living. But there are 2 billion people on this earth with no access to electricity. And they have an enormous yen to be a part of the electric club. And when there is demand, supply will come. So electric production is expected to increase more rapidly than other forms of energy for some years to come. Oil and gas probably will become more and more expensive. Nuclear power, however, has not grown very much. Worldwide, about 16% of electricity is nuclear produced. Due to concerns about possible radiation leakages, accidents, and radioactive waste disposal, nuclear power has not grown as expected, although about 60 plants are currently under construction worldwide. Wind power is growing in windy areas and is useful, but unlikely to become a major contributor to the world's power needs. Solar power is a possibility. It's available but relatively high-priced. Panels in space could theoretically collect solar energy and beam it down to Earth, but the practicality of that concept is unconfirmed. The sun's energy is created by the fusion of atomic nuclei in the solar interior. So indeed, most of our energy here on Earth, coal, oil, wind, hydro, they all owe their existence to the nuclear fusion in the sun. And ever since humans have begun to understand the process, they've wondered if it would be possible to duplicate it here on Earth. For half a century, nuclear engineers and scientists around the globe have been striving to develop fusion power, and success has been elusive. But some progress has been made, and it seems likely that an effective fusion reactor can be built within several decades. There are a number of reactions which are possible for fusion. Each of these reactions has its own characteristics, advantages and disadvantages. In most existing nuclear power plants, fission plants, nuclear fission plants, and some of the possible nuclear fusion plants, which don't exist yet, the nuclear reaction is nothing more than a heat source used to make steam, which turns a turbine, which drives the generator. But fusion specialists point out that reactions using the isotope of helium, helium-3, have some particularly interesting characteristics. One helium-3 reaction, the reaction products could be converted directly to electricity, eliminating the need for the steam and the turbine and the generator, providing high efficiency and relatively low capital costs. Additionally, compared to today's nuclear fission plants, it produces a relatively small amount of radioactive waste. A different helium-3 reaction produces lower energy generation, but no radioactive waste whatsoever. So both of these ideas look promising. There is one small problem with helium-3. We don't have any. Well, there is a tiny amount in normal helium and in natural gas, and a small amount is produced in the maintenance of nuclear weaponry, but not nearly enough to power a nuclear plant. Astronomers believe helium-3 exists in large quantities in the atmospheres of the giant planets, Jupiter, Saturn, Uranus, and Neptune. But fortunately, we're not required to go that far to get it. Helium-3 is created in the sun's interior. It's a minor component of the solar wind, that eternally streaming wind that streams outward from the sun in every direction. It's been captured in the soil of the moon. We found it in the Sea of Tranquility on Apollo 11. It's been estimated that 1 million tons or more of helium-3 are resident in the lunar topsoil. That could provide enough electricity to power the planet Earth at today's usage for 100 centuries. So the proponents say there exists the probability of a clean, safe, non-polluting, non-radioactive energy source that could operate for centuries, and it could be operating in a few decades if we get serious about doing the necessary development work. They believe we cannot afford not to move forward on this. Wait a minute, the critics say. After a half-century of trying, we have not been able to build even a prototype of a commercial-type fusion reactor. We don't really know that helium-3 exists in the moon in those quantities, and even if it does exist, we don't really know if we could extract it and deliver it back to Earth economically. They tend to believe that we'd be better off to make other investments to move toward the hydrogen economy. Now, the principal component of the hydrogen economy is the fuel cell. We first used fuel cell in the Gemini spacecraft when we couldn't afford the weight of regular batteries for the power load and the duration of flights that we were flying. And fuel cells have provided electricity for manned spacecraft ever since. They're more efficient than today's gasoline, diesel, or even hybrid power plants for cars. A number of development programs for fuel cell powered vehicles have automobiles and buses being road tested at various places in the world today. You might watch the futures price on platinum. Fuel cells don't work without platinum-type catalysts. And apparently platinum is somewhat in short supply. Worldwide platinum usage is up every year and supplies are going down every year. Pundits maintain there just is not enough platinum or other similar rare metal catalysts to provide enough fuel cells for the automobiles and other vehicles that a hydrogen economy would require. Responsible studies have indicated that with a major effort, we could switch over to a hydrogen economy in just 3 decades with an 80% reduction in oil consumption, assuming sufficient catalyst material was available. And because the current high prices of crude oil, there is a strong motivation in many quarters to initiate development projects on alternative energy sources. There have been some concerns about handling massive quantities of hydrogen. It's a small molecule, so leakage can be a problem. It's highly combustible and requires care and stringent procedures to provide unintended ignition and explosions. It has, however, been used successfully in a variety of applications with acceptable safety levels. There is another idea worth examining. It's related to meteorites. And as many of you certainly know, meteorites are meteors or shooting stars that are big enough to survive their atmospheric plunge and reach the surface of the Earth. And there are a lot of them. Due to meteorite accretion, the Earth becomes heavier every year. Apparently how much is difficult to determine. I've seen estimates from 10,000 to 350,000 metric tons increase in Earth's weight each year. Most meteorites are rocky or stony. Some are stone and iron. About 1 in 20 is an iron meteorite, so-called because it is principally iron with substantial amounts of nickel and copper and sprinkling of other elements. It's not escaped attention that some of our most productive nickel and copper mining occurs where large meteor craters exist or have existed in the past. This suggests that rich ore may exist because the object that caused the crater was an iron meteorite. I don't know that this has been proven, but the logic seems reasonable. Some of the best platinum mining is, in fact, in and around such meteor craters. Unfortunately, most of the craters on Earth have been lost to millions of years of crustal fracturing and erosion. Craters on the Moon, on the other hand, have had very little disturbance for the past couple billion years. There are about 1 million large craters on the Moon, and about 30,000 of them were probably caused by impacts of large iron meteorites. Based on our experience with such craters on Earth, we can expect substantial amounts of metals to be recoverable, including those like platinum that we need to make the hydrogen economy hum. Advocates of lunar mining say that alone is worth going back to the Moon. Critics say the existence of platinum on the Moon is unproven, and mining operations on the Moon will be very expensive. They say it would be better to develop alternative catalysts or fuel cell operating techniques here on Earth. Return to the Moon advocates believe that the Moon provides extraordinary opportunities for continuing the scientific investigations that have been so fruitful in the past half-century. But they believe that the most important reason to return is to help solve the problem of energy needs on Earth, helium-3, platinum, or lunar resources that may be vital to our future, and we need to do the prospecting as soon as possible to see that the promise is met. The master plan is to continue on from the Moon to Mars and beyond. I think there's substantial enthusiasm for going on to Mars. And a Mars flight, as you all already know, has some very interesting characteristics. I'd like to talk about a few aspects that I haven't yet talked about. To understand these characteristics, you have to go back in history with me, quite a way back, 4 centuries, to a town in southwestern Holland, Middelburg. The spectacle maker in Middelburg was one Hans Lippershey. The story is told that across the street from his spectacle shop was a butter and egg shop. And above the butter and egg shop was the bedchamber of an attractive and provocative milkmaid. Now, the young apprentices of Herr Lippershey were fascinated with this milkmaid and the views that could occasionally be seen through her window. Now, it's impractical to speculate on the consequences of this light-hearted lechery, but it's reasonable to assume that without it, I would not have heard of Lippershey, you would have not heard of Armstrong, and I would not have the pleasure of being invited today. The young apprentices, in their zeal to improve their vision, found they could arrange spectacle lenses in such a way that distant objects, such as milkmaids, appeared substantially closer. So it happened that the telescope was born. It was just an oddity at the time, first manufactured as a toy. Not until the concept of this new telescope found its way across the Alps, and Galileo Galilei pointed his version toward the heavens, was it recognized that the human eye had gained an entirely new perspective on the immensity of the universe. Galileo's observations of the moon revealed facts that completely upset the common beliefs of the time. The moon was a smaller sister planet with mountains and valleys, and Jupiter had moons The sun had spots on it, spots that disappeared around the eastern rim of the sun and reappeared around the western rim. The sun was a rotating planet. The whole concept of our universe was wrong. Copernicus, in his contention that the Earth was not the center of things, might just be right. Well, the Roman Church was substantially upset with Signore Galileo and his ideas. His assertions were contrary to the teachings of the Church. Facing the Inquisition and a rendezvous with the stake, Galileo recanted. He denounced his theories. Recognizing Galileo's brilliance, the Church wanted to hedge its bets and constructed astronomical observatories at a number of its monasteries across Europe. Astronomy is nice, clean work, but it's principally a night shift job. And monks did not get a bonus for working at night. So in a flash of brilliance, someone came up with the idea of an astronomical day job, studying the spots on the sun. The monks charted the size and frequency of these sunspots, and within a century or so, they properly concluded that the sunspots peak in intensity every 11 years. By the 20th century, we knew these sunspot peaks were dangerous. They put out enormous magnetic storms and radiation. Here on Earth, we're protected from all these troublemakers by the Earth's magnetic field and our atmosphere. But out in space, you're running naked. So back in 1961, when the young President John Kennedy proposed that the United States should go to the moon by the end of the decade, he had no idea that some poor spaceman was going to be in for a big surprise. The end of the decade would put him precisely in the middle of the sunspot cycle peak. But we Americans were in a race with the Soviets, trying to go to the moon. Even if we were in the peak of the cycle, we were not going to let a few sunspots keep us from being in the competition. Actually, sunspots were not the real concern. It was those sinister solar flares. Solar flare is a gigantic solar storm with an energy release equal to millions of hydrogen bombs. Solar flares put out radiation at a prodigious rate. Protons, electrons, hard X-rays, gamma rays, miscellaneous other bad stuff. And solar flares occur most often at the peak of the sunspot cycle. In Apollo, we were mainly concerned about the high-energy protons emanating from these solar flares and prominences that we should certainly expect. We were extremely limited and certainly could not afford the luxury of equipping our craft with layers of lead shielding. What to do? The best shield we had on board was the fuel in our fuel tanks. Amateur astronomers volunteered to monitor the sun for sunspots and solar flares. Arrangements had been made for them to communicate such sightings immediately to mission control. So we had help from amateur sun gazers all over the world. They watched for solar flares. It was supposed to work like this. A big flare occurs, but it's night in the Western Hemisphere, so nobody from Alaska to Argentina ever saw it. The area around here, all the Mediterranean and Southern Europe was under clouds, so nobody here could see it. But there's some blue sky over Scandinavia, and Mission Control gets a telephone call. It says, "Hello, Houston, this is Anders Svensson. I just saw a giant solar flare. I think you better tell Apollo." And they would do that. mission controller called immediately. Now, the sun's high-energy protons travel at approximately 43% of the speed of light. And they would arrive at the Earth-Moon system about 10 minutes after the flare was observed. That could provide just enough time to reorient the spacecraft so that the fuel tanks were between the crew and the sun and would shield them from the bad stuff that was headed their way. It was an imperfect solution, but it was the best we had. And we were blessed with good luck or divine providence, because I'm delighted to be able to say, during each of the Apollo flights, we never encountered a major flare. We never had the requirement to utilize the procedure. No flight ever recorded a worrisome level of radiation. In 1989, a huge solar flare left 6 million people without power. In 1998, a flare was blamed for interrupting mobile phone service to millions of customers, even with the Earth's atmosphere and magnetic fields serving as a radiation insulator. 11 years after Apollo, at the next sunspot peak, a solar flare erupted that would have given an unprotected spacecraft crew like ours an exposure of 2,600 rem, more than 5 times the lethal dose. Mother Nature occasionally makes a very effective effort to remind us who's in charge. Clearly the risk is real and substantial. During slow periods in Apollo 11, when we had the cabin darkened, I occasionally saw what seemed to be sparks or microscopic lightning flashes. And my crewmates soon noticed the same thing. We attributed it to some sort of high-energy particle that was striking the structure inside the spacecraft. Post-flight analysis concluded this was indeed Cherenkov radiation, high-energy particles, but they were not hitting the spacecraft. They were penetrating our eyes, and we were seeing the flashes on our retina. For a Mars trip, the crew will spend a lot of time in that no man's land between planets, subject to full bombardment from galactic cosmic rays, gamma rays from black holes, and the protons from the occasional solar flare. For this duration, cosmic rays become a concern. Intergalactic nuclei have energies of millions of MeV, 100,000 times that of a solar flare proton. Spacecraft weight is always at a premium, so lead shielding is probably not possible. We really don't know the effect on humans of this kind and duration of radiation exposure. So when we go to Mars, we will have to probably need some sort of material to absorb or deflect this energy. And in fact, there are a number of possible shielding techniques that, with a bit of development, just might be able to do that job. So Mars trip definitely will not be an ultra-safe trip, at least initially. Nevertheless, I do believe it's doable. I'm certain that the unknowns for such a flight are far fewer than we faced when we began Apollo 44 years ago. In turning unknowns into knowns, that's the essence of science and exploration. Like installing a mirror on the moon to find the proper location of Mount Hamilton. And whatever happened to that experiment? It's still operating. 35 years later, the mirrors are still reflecting lasers from observatories around the world. And the results are surprising. The accuracy That distance has improved over the years from that initial 28 centimeters to now about 1 centimeter. The moon is moving away from Earth at an arrestingly specific rate of 3.8 centimeters per year. The motion of plate tectonics is now measurable. The distance between Europe and South America is changing and can be measured. Oscillations in the measurements indicate that the moon is likely to contain a liquid core, and there are variations in the length of the day here on Earth due to tides and motions of the Earth's core up to 1,000th of a second. The mirrors have confirmed the equivalence principle of Einstein's theory of relativity, but call into question the adequacy of general relativity to accurately describe the motion of the Earth-Moon-Sun system. But the mirrors are expected to continue to be busy for many years to come, which gives me enormous satisfaction as a technician on the project. Today, Discovery rests on a launch pad in Florida, hoping to return to the International Space Station. I hope you'll join me in wishing it success. I thank you for being here. I appreciate you giving me the most valuable gift, your time.
Vamos a hacer un pequeño receso de 5 minutos. Enseguida empezamos con las preguntas para Neil Armstrong de los diferentes participantes en Campus Party que hemos traído hasta aquí y también de unos cuantos que van a entrar por videoconferencia desde la Campus Party en el recinto de Feria de Valencia. En 5 minutos las preguntas. Gracias.
Microphone for the questions by video conference.
Bueno, vamos a ir ya con las preguntas. Os cuento cómo lo tenemos preparado. Por favor, tomar asiento, que vamos a ello. Estábamos un poquito bajitos, sí. Bueno, os cuento cómo tenemos preparado, mientras vais tomando asiento, el tema de las preguntas, ir sentándoos, ocupando los lugares. Obviamente no podíamos traer a más de 5.000 personas a este auditorio y lo que hemos hecho es, ayer, poco después de la ceremonia de inauguración, formulamos en nuestra web de campus un reto a los campuseros y era que hicieran preguntas. ¿Qué pregunta le harías tú a Neil Armstrong? Y lo que hemos hecho es una selección de las mejores preguntas. Hay unos que van a entrar por videoconferencia, que están ahora en el recinto de Feria de Valencia. 5 personas en concreto. Ya tenemos la primera que me tiene que estar oyendo y está en pantalla. ¿Me estás oyendo? Hace así el hombre.
¡Que si me oyes!
¿Estamos?
¿Me oyes?
Sí, se ríe. Bueno, teóricamente nos está escuchando. Vamos a hacer esas 5 preguntas, luego haremos también algunas preguntas de campuseros que hay aquí, que hemos traído. ¿Hay campuseros aquí? Sí, no lo sé. Y si hay tiempo para más seguiremos y si no, pues ahí lo dejaremos. ¿De acuerdo? Así que, si estamos preparados, Manolo, que nos va a hacer de traductor con su excelente inglés, vamos a realizar ya la primera pregunta desde Campus Party. Atención, campusero, cuando quieras. Vamos a intentar a ver cómo nos queda esto con el servicio de videoconferencia de Telefónica. Adelante.
Buenos días, señor Armstrong. ¿Qué opina usted de la polémica entre los que consideran la ventaja de enviar vuelos tripulados y los que opinan que es mucho más rentable enviar zonas espaciales?
Es que no lo oímos bien y Manolo es el que tiene que traducir, así que vamos a repetir la pregunta y Manolo la formulará. A ver, ¿me escuchas? ¿Puedes venir, por favor?
Él lo ha oído.
¿Es eficaz enviar vuelos tripulados contra los que piensan que es mucho más rentable enviar zonas espaciales?
Vale, ¿estás ahora? Vale, ahora me escuchas bien. Vale, pues venga. Formula la pregunta, Manolo, y Manolo se la escucha. Vale, que el altavoz no funciona, pero este sí, y Manolo lo escucha. Formulamos la pregunta. Perfecto.
Thank you for the question.
La pregunta es si, ¿qué opina el señor Armstrong de la polémica que hay entre si es mejor hacer vuelos tripulados o vuelos automáticos que de alguna manera eliminen muchos de los riesgos que tiene y de los costes asociados a los vuelos tripulados?
Thank you for the question to discuss manned and unmanned options in the space flight. First, I am a great advocate and supporter of unmanned flights. They provided Apollo with many useful pieces of information that were required for us to be able to go there safely in a manned craft. Additionally, unmanned craft probes can go many places that man cannot go. The radiation environment in the area close to Jupiter, for example, can be reached by an unmanned craft, but not by a manned craft. Unmanned craft are useful, but the amount of information they can gather is limited. And they're less reliable than manned craft. Let me give you an example. I think we've had about 31 or 32 flights to the moon, to Mars. I'm sorry, 31 or 2, maybe 33 flights to Mars. 2/3 of those have failed, and 1/3 were successful. So they are certainly less expensive than a manned flight when they work, but the returns are poorly when they fail. And additionally, the amount of information that a man can acquire on a flight far outweighs that the unmanned craft can do, mostly because the unmanned craft cannot identify unusual situations that a person, a human being, would immediately think was of substantial interest, but the unmanned craft has no way of knowing that. Consequently, it takes a combination of both, and I foresee that we'll continue to have wonderful results from the unmanned craft as they go further and further into the solar system and outside the solar system.
Ok, vamos a formular la siguiente pregunta que está haciendo el siguiente campusero, que va sobre algo relativo a Pedro Duque. Null está escuchándolo dentro de los auriculares y vosotros estáis escuchando la traducción simultánea también, por lo tanto.
La pregunta es si es verdad que desde el espacio se puede observar perfectamente la diferencia que hay en la Tierra, visto desde el espacio, la diferencia que hay entre países pobres y países ricos.
In my flights, I did not observe the economic differences on Earth. You certainly are able to observe the geographic differences and weather differences. You don't see boundaries between countries from space, but you see the ocean and the landforms and the vegetative differences between the countries with areas with lots of rainfall and those that are deserts. And of course, the most obvious are those that are covered with snow, like Greenland and Antarctica.
Un nuevo campusero, en este caso campusera, que va a formular otra pregunta que Manolo ahora lo va a formular a Neil Armstrong. La traducción la estáis escuchando bien, ¿verdad? ¿Los auriculares? Sí, perfecto.
Si volviera al espacio, ¿qué planeta le gustaría visitar?
Question is which planet would I like to go to next, and definitely it is Mars. It's the most available, the closest, and the friendliest, and I just can't wait to meet the people that live there.
Bueno, vamos con otro campusero que está formulando la pregunta. Y Manolo se la formula ahora, Neil Armstrong. Ok.
La pregunta es: ¿qué beneficios puede tener para la humanidad el que el hombre vuelva de nuevo a la Luna?
I tried to explain in my presentation today some of the resources of the moon which may become important to man's survival here on Earth. Of course, we don't know enough to know for certain that those are true, but I think we have strong indications that they are possibilities, they may be important to us. The scientific community would like to go to the moon because there are a lot of things they would like to do, particularly on the back side, the side away from Earth, where they have substantially less radio emissions and radio interference.
Muy bien, vamos con el último campusero que entra por videoconferencia desde la Feria de Valencia, donde hemos dormido muy poquito esta noche, os lo puedo asegurar. Ha sido tremendo esto. Casi ya tenemos una voz de hombre. Luego iremos con las preguntas de los campuseros aquí, por favor, estar preparados.
La pregunta es: ¿qué nuevas puertas se están abriendo para la tecnología espacial y qué opina de lo que esto puede ocasionar, puede producir?
Well, there are many new technologies which have provided enormous benefits to space exploration. The one that of which this audience is most familiar, of course, is in the area of computers and information flow. I would just mention to you that we had in my younger days we had no digital computers to use because they were so slow. So we used all analog computers, which were lightning fast, but not very accurate. The first digital computer on a spacecraft was on the Gemini, which I flew. It had no screen, no sound, no alphanumerics. It had keys 0 through 9, read, clear, and enter. And it had for the information for the computer to give information to the operator, it had one 7-digit register, all numbers, no letters, two numbers for identification and 5 numbers for data. It had not 4 gigs, not 4 megs, it had 4K. Yet we were able to navigate in space, calculate corrections to our orbits, rendezvous with another spacecraft, and fly an entry back to the Earth's surface and land at a prescribed landing point, all with a 4K computer. Do you think you've made a little progress since then?
Bueno, nos quedan 5 preguntas de 5 campuseros que hemos traído. A ver si Silvia me indica dónde están. Por aquí. Voy con el micro. Vale. Vamos por aquí. Ponte de pie. Anda. Un aplauso para la campusera que va a hablar.
I think that I'm fortunate to be here, having the opportunity to make you a question. So that is. En toda su vida relacionada con la astronomía, ¿qué es lo que nunca le han preguntado y le hubiera gustado responder? Ya sea sobre anécdotas, sensaciones, sentimientos. ¿Qué es lo que le hubiera gustado contar y no ha tenido la oportunidad hasta ahora?
Oh, there's you. Yeah.
Okay. ¿Qué le habrán dicho?
That's a good question.
I'm thinking. I've answered a lot of questions, and I'm sure there's someone wanted to have people ask and they never did, but my memory is so poor I can't remember what they are.
Bueno, vamos a hacer otra pregunta.
Mi pregunta es, ¿por qué se siente más satisfacción? ¿Por haber podido ser la primera persona en pisar la Luna o simplemente por haber pisado la Luna?
This probably will surprise many, but I was principally an engineer and an aviator, test pilot. And pilots always like to make smooth landings, but they don't think very much about getting down off the aircraft and walking around on the ground. That's not a focus that they have. Consequently, I really never thought that the walking part was particularly important. To me, the final approach and landing was far more difficult. It was fraught with unknowns, and the systems were heavily loaded. Parts of the algorithms we were using in the computers had been tested on Earth, but never in the environment of space. And consequently, we thought on a difficulties of a 10-point difficulty scale, the descent and landing was 11 or 12. And on walking around on the moon, it was 1.5. So that's what we considered the challenge, and that's what we were so pleased with being able to accomplish.
Buenos días, señor Armstrong. ¿Qué pensaba cuando sobrevolaba con el Apolo la soledad de la cara oculta de la Luna sin ningún tipo de contacto con la Tierra? ¿Cuáles eran sus sentimientos?
What were my feelings on the backside of the moon? When we were in communication with Earth, anytime we could have line of sight access to Earth, people were always talking to us. They were sending up information or questions, and we were always busy writing down notes from things they told us. And when we got on the back side of the moon, which is not, by the way, always dark. It's sometimes, it was actually the backside of the moon while we were there was half light and half dark. But it was, to be on the backside was a great relief. We took off we never heard all this conversation, and we could just rest and enjoy the scene.
Una pregunta del profesor.
Sí, señor Armstrong. En la carrera espacial y en el programa Apolo, evidentemente, hubo un componente de prestigio político muy importante. Usted ha planteado un regreso a la Luna en búsqueda de materias absolutamente estratégicas. ¿Cómo cree que deberían preverse y gestionarse los posibles conflictos políticos y esperemos que no militares que plantee ese regreso a la Luna?
It's an excellent question. This country and my country are both signatories to a treaty, which I think was signed in 1967, which made the moon an international property. It could never be claimed by any individual. And you'll recall, no, you probably won't, you may recall, some here in the audience will recall, most were not alive at the time this happened, but when we reached the surface of the moon, we made no claim there. And so, as a matter of fact, we noted the fact that it belonged to humanity and not any particular nation. And so long as we are countries that are believe in rule by law, those conflicts should not occur. That's not to say they can't occur, because people that do live by law occasionally act outside the law. So, but to the extent that we can be protected by common interests and agreements, it will not happen.
Yo creo que esa pregunta tiene una fácil respuesta. Todo el mundo sabe que la Luna pone acción. Voy a preguntar.
Hola, buenos días, señor Armstrong. Mi pregunta es que usted es un magnífico fotógrafo en su misión de Apolo 11, pero solamente usted salió en una foto panorámica que utilizó un barrido el señor Armstrong en un lado del módulo lunar. ¿En algún momento usted le pidió que le hiciera una foto en primer plano?
My colleague, Mr. Aldrin, was far more photogenic than I was. So we took all the pictures of him.
Manolo, yo quiero aprovechar la oportunidad, si es un fan menor de él como yo, de que tú le formules una pregunta. Tú has estado literalmente muchos años persiguiendo a este señor para que estuviéramos hoy aquí. Para nosotros es increíble, ¿no? Así que Manolo.
I will translate you, but I have. La pregunta que yo le haría, no está preparado, pero así improvisando, la Luna, las hazañas, las leyendas vivientes, son acontecimientos que nos permiten ver la dimensión de lo que la humanidad va consiguiendo a través de personas aisladas que muchas juntas hacen que el mundo sea mejor. La pregunta que yo le haría a cualquier persona que trabaja en el mundo de la conquista espacial es ¿cuándo conseguiremos que todo lo que se haga en el espacio tenga una finalidad, como él ha expresado en su conferencia, estrictamente científica y benefactora de la humanidad, y nos olvidemos del aspecto militar. ¿Será posible alguna vez?
Well, we can hope so. We can hope that that intellectual power and logic and desire to improve our human race and its future will overpower those differences which cause us to begin armed conflict. And I think there may be hope in that direction. We've made in your field, in science and technology and computers and information technology, we have seen astounding progress in the past century. And if we are to survive as a species and to persevere, we need to make equal progress in the human brain and character. And I'm hopeful that that will be done. I hope that will be the great improvement that we mark the 21st century with. And if so, our future can be bright. If we fail to do that, we are going to have some dark days ahead. I want to thank you all for your kind attention, your courteous questions, and as I said before, for your valuable time.
Thank you very much. Muchas gracias a todos. Ahora vamos a ir a la inauguración de la Campus Party Experience, que sabéis que está en la sala Arquerías, donde normalmente montábamos la Campus Party, así que os invito a todos a que vengáis con nosotros, saliendo del pasillo y yendo un poquito hacia la izquierda hasta el Salón de Arquerías, que está justo aquí detrás. Gracias.